And hello everyone, I am Aditya Koranga. It's nice to see you all. And today we are going to talk about one of the most important topic these days, post-quantum cryptography. So the title is Why Post-Quantum Cryptography, PQC, is critical for digital security today. Now, before I start, I want to know how many of you guys are aware about this term PQC, or maybe you have heard it a couple of times before. Okay, one. That's good. And yeah, that's me, Aditya Koranga. And basically, I am the Technical Advisory Committee representative for individuals at OpenSSL Corporation. OpenSSL is, as you guys know, is an open source library that provides cryptographic tools as well as the TLS implementation. Now, I wanted to create a dedicated slide on my introduction, and I did try to make it, but I got a bit lazy within the process, so I had to ditch that slide. But anyways, as you know, I'm the technical advisory representative for OpenSSL Corporation, and I also work as a principal security architect in a company called PQStation, which is based out of Singapore. And I also own a non-profitable organization in India that is called NgKore Foundation. Now, my work in PQC started 5 years back when I was doing some college thesis on PQC. And apart from that, I've played a various role in my life. I used to do teaching as well. One of my childhood dream was to, when I was in kindergarten, my childhood dream was to marry a girl who used to stay like in a nearby area. Then my plans got changed. I wanted to become dancer. Then I wanted to become a chess player. And then I ended up with PQC. So I don't know how I ended up here. So anyways, before I start, I would like to start with the mission of OpenSSL, basically what vision we have. So we believe everyone should have access to security and privacy tools, whoever they are, wherever they are, or whatever their personal beliefs are, as a fundamental human right. And yeah, so basically PQC, before talking about PQC, we need to set the background. Why do we even need PQC? So there are a lot of people have been working in quantum computing for decades now. And recently it got the spotlight because of the threats that it's going to bring up with the recent advancement. So some of the quantum computing advancements you guys might have heard about is like the one is from the Google, that is quantum ecos. So Google has developed a quantum chip called Willow, and they did like one of the first ever algorithm that was verifiable by quantum computing, and it was like 13,000 times faster than the latest supercomputers these days, right? And then Microsoft developed Majorana 1 chip. It's also one of the biggest achievement in quantum computing area. And then IBM recently came up with Nighthawk. It's considered to be the strongest quantum computer so far. And then within Japan, now Japan backs quantum startups. I think it invested something like 50 billion yen to do the quantum computing stuff. And then recently, you might have heard about some collaboration between Fujitsu and Riken regarding the fully domestically produced quantum computers. And interesting enough, day before yesterday, I was in an event in India. So it's called an AI Summit. And in the booth of Fujitsu, I saw this dummy quantum computer that they brought. So the thing is, like now Japan also is doing a lot of stuff when it comes to quantum computer. Earlier it was mostly into like IBM, Google, and different countries were investing a lot. But now Fujitsu is doing a lot of good stuff, so it's good to know. Now these are all fancy things that are being done in quantum computing area. Like they run on qubits, not the simple bits, not 0 and 1. It's like both 0 and 1 at the same time. So the computing becomes much faster because now we are not going like 1, 2, 4, 6, 2 to the power. Now we're not going like 1, 2, 3, 4 like this, right? Now we are going 2 to the power 0, 1, 4, 8, 16. So it's going into 2 to the power n process. Yes. Now why post-quantum cryptography? So quantum computer brings with a lot of advancements, like in areas of areas which need very high computation, fast computation, and it's like now in the medical area also the quantum computer will bring a lot of good stuff, you know. Now, okay, we understand that quantum computers have a lot of advantages, and it will do even much better when it comes to computing as in general. But quantum computers, since the computation is really faster, it has a threat called quantum threats, which says that it is going to break the current security. Like our internet depends on digital security, cryptographic algorithms, security protocols. Now all those things will be compromised if we bring up like a very strong quantum computer, right? So just for the set the base and introduce about PQC, what basically it does is, for example, you have Alice and Bob, they are sitting over internet, and they are communicating, and this is what everyone does, sitting over the internet and communicating, sending messages. Now these messages could be like very critical, very important. Now, but we don't care, because we know the security, that network security, the protocols that we are using is completely secure. But it was it was supposed to be that way until this quantum computing and quantum attacks, idea of this quantum attacks come into the picture. Now, what we know is like all the communication that we are doing over the internet securely is secured by public key cryptography. So public key cryptography is like you using public key, private key, you are encrypting, decrypting, right? Those sort of stuff. Now, the thing is, now all these messages are secure because they are going in an encrypted format. So if someone else wants to look into the communication that is going on between Alice and Bob, it will be like a non-readable form. It will be like random bits that you can't really identify what actually they are talking about, right? So this is all completely secure using the public key cryptography. Now let us suppose we bring a quantum computer, and it's just not a simple quantum computer. It's a very strong quantum computer that we call cryptographically relevant quantum computer, sometimes also known by the name CRQC. Now, quantum computing advancements are being done, but it's not still in the stage that it can break the algorithm, the public key cryptography that we are using right now. But we are assuming that later in, like, let's say in 5 years, 10 years, 6, 7 years, whatever, quantum computer will come which is cryptographically relevant. Now this quantum computer can actually affect the security, the cryptography that we are using, right? And using this CRQC, what will happen is the data, the communication that was going in was done in a encrypted format. This will be compromised, right? So all the text that you are sending, all the critical information that you are sending from point A to point B, those will all be decrypted using a cryptographically relevant quantum computer. So that answers the question, why post-quantum cryptography? And it's just not like a simple message going on between Alice and Bob. We use our public key cryptography in everywhere, whether it's your protocols like TLS, VPN, SSH, public key infrastructure, SMIME, OAuth, even for the authorization part, FIDO2, etc. All these protocols or frameworks uses public key cryptography throughout the whole process. Now, the attack vector, the blast radius, is much more higher than we are just saying, okay, just a single communication, that much will be affected. It's just the tip of the iceberg. All these network protocols that we are using in our day-to-day life, these all will be compromised somehow, right? And you guys know, if I zoom in a bit, if you guys can look into this, you might notice some terms like RSA, elliptic curve Diffie-Hellman. So these are like the security cryptography that our internet is widely depends on. So these algorithms are used like throughout everywhere. Now what you can see is like these transition part, these algorithms like RSA, they will be deprecated out after 2030 and completely disallowed by 2035. And this is from the document from FIPS and NIST. And we all know, like in cybersecurity, in cryptographic world, we follow NIST widely, like every time. So as you can see, these algorithms, these classical algorithms will be deprecated, disallowed by 2030 and 2035. So that means the transition that we need to do for newer algorithms is right now. The time is right now. This time frame is very critical because you know like the earlier transition from SHA-1 to SHA-2, SHA-3, it took 25 years, and it was it took us comparatively larger time to do this transition. Now, why I'm showing this? Just to get you notified about what actually is going on in this cybersecurity world or cryptographic world these days. And now, what is post-quantum cryptography? Okay, now we have realized why we need post-quantum cryptography, because all the algorithms that we are using right now, the public key cryptography, will be deprecated and disallowed in few years. Now, what actually is post-quantum cryptography? So PQC is like the new set of cryptographic algorithms that are designed to secure digital systems against future and powerful quantum computers. So all that threat that we talked about, all the algorithms that we said are now not that strong enough to be secure against the quantum attacks. So for that reason, now we need PQC, post-quantum cryptography. And there was a whole process of identifying what these cryptographic algorithms are, and it started with like several algorithms, and we still say, okay, we have a list of 7 to 10 algorithms that we say, okay, these are quantum proof, quantum secure, but it's like, it's not the thing that if I say it's quantum safe, it will be quantum safe. We need some standardization, we need some specifications. So now FIPS, you guys might know about FIPS. These are the standardized body from NIST that provides the cryptographic algorithms, all the standards regarding cryptography and cybersecurity. Now FIPS came up with 3 algorithms that are now standardized according to NIST. These are FIPS 203, 204, and 205. These are just a number, and the algorithm name is MLChem, MLDSA, and SLSDSA. So FIPS 203 talks about MLChem, FIPS 204 talks about MLDSA, FIPS 205 talks about SLSDSA. So these are the So these are the new algorithms, these quantum safe algorithms. These are the standardized post-quantum cryptography algorithms out of several other lists that we say, okay, these are the algorithms that are quantum safe. But now the standardized body and the industry are adopting these 3 ones, MLChem, MLDSA, and SLSDSA. Right? And please remember those terms, MLChem, MLDSA, SLSDSA, because throughout this whole presentation, we will be talking about those terms like quite a while. Okay, quite so many times. We'll take reference of those terms. Now the thing is, you might argue with me that, okay, as I said, you will just repeat my words, that cryptographically relevant quantum computers are still not there. Then why do we even need to care about post-quantum cryptography? Let's say if I say it will take 2035, 2040 to have a very scalable quantum computers that can break the current algorithms. But the problem is not that. The bigger problem is harvest now, decrypt later. Let's say we have, someone is collecting our data and it's in encrypted format, so we don't worry, okay, if someone is collecting this data, then let it be. It's all in encrypted format. Nobody is going to take any, nobody is going to compromise whatever they collect. Nobody is going to take advantage of the collected encrypted data. But let us say a quantum computer is available later in the future, okay, let's say 2035. Now, what that quantum computer can do is, it can decrypt all the encrypted data that was collected as of now. And this is not just my thinking. The encrypted data is actually being collected in so many countries. A lot of people, their dedicated job is to do this only, to collect the encrypted data. Now, all those bunch of chunks of encrypted data is there. And if in future quantum computer is available, all that data that was collected will be decrypted. Now, these are not simple text conversation. Let's say some military information, that the communication that they are doing over the secure channel, those are being collected. Let's say some banking, finance information, transaction information, all that data in encrypted format is collected. Now, all that will be decrypted. So what can we do now? The best thing we can do now, by the way, all these data will be decrypted. And let us say the data is still there, and what we will do now is we will adapt PQC right today, right after this talk in 2026, right? Now, what changes will it bring with this adapting PQC today is the data from this point, right after 2026, all that data will be protected even when there is a quantum computer, right? Even if this data is encrypted using PQC today, the data right after this point will be protected no matter how strong quantum computer you brings in. And yeah, so all this data from this time will be secured now. And I'm really sorry to say that the data that is lost here will be decrypted. But the good thing is, after this point, the the radius of data being decrypting is much lesser than as compared to the first case, right? Now, this is, so you might have right now you might have got the idea of why adopting PQC from this point is important, right? Now, this is just not like a thesis. It's actually being widely discussed and widely adopted throughout the world. And some of the initiatives that are being taken right now or have been taken before are like this. So all the major countries are now working on this post-quantum migration stuff, like replacing those classical algorithms that we're using right now with the newer set of algorithms that are the PQC, post-quantum cryptography algorithms. So you can see some countries name like Australia, they have post-quantum initiatives, and they are saying that they want the transition of this PQC transition by 2028, and they want all their system to be fully migrated to PQC by 2030. You know, and they are like, I think they are really brave to come up with this timeline, but it's going to be very tough, I think. And yeah, so and Canada has also came up with the CCCS guidelines, and they say by 2026 we need to prepare, by 2031 we need to start the transition, and by 2035 we need to have full transition to PQC. So all the area in which we are using security protocols, classical cryptography, that needs to be migrated with the newer post-quantum cryptographic algorithms. And China has come up with the NgCCC initiative, where they are trying to bring up their own PQC, own homegrown developed PQC algorithms. So these are all the timelines. In major of the cases, you can see 2030, 2035. So just to collect all this data, I think by 2030 and 2035, you need to have like full PQC migration. And since we are in Japan right now, so Japan has come up with this cryptrec guidelines, in which they have not told about like a specific timeline as of now, but they are saying, okay, we need to start planning from 2025. And actually the work is being done, because in cryptrec, I'm sorry if I'm butchering the pronunciation, cryptrec, they have a PQC working group, which is majorly focusing on these stuff. Right? And Singapore is working on CCA guidelines, and a lot of funds are being invested, are going for these initiatives. And you can see there is terms like QKD. QKD is another technology in which you use quantum computing devices to save the to have a secure channel, but that is, I think, not going to be widely accepted as of now. So in major of the cases, we are going to transition with PQC, post-quantum cryptography, right? And once again, see the timeline 2030, 2035. In order to reach the timeline, we should have started from like 2-3 years ago. And, but still, yeah, I think if as soon as you start this transition, it will be good. Cool. And you guys remember there was a list of security protocols that I mentioned, right? So in all that cases, PQC migration is being done. And in some cases, this migration is already been done. And one of those protocols is TLS. In the various example, real life example, one of the quickest migration was that was seen with any security protocol was TLS, transport layer security. For example, some proofs are like AWS, KMS, certificate manager, and the AWS CloudFront. It's like a CDN. They have already integrated this MLCAM, post-quantum cryptographic algorithm. Kubernetes, which is widely used, is now by default using post-quantum cryptography between the pod-to-pod connection or between the control plane connection. Sorry, not for the pod-to-pod connection, but at least for the control connection. If you use Kubernetes 1.33, by default you can see it is using MLCAM. And Akamai, in their CDN, they have PQC by default, like hybrid PQC. And this is this is the screenshot taken from one of the blogs from Cloudflare, in which they say like now 51.1% of their HTTPS traffic is now secured with post-quantum cryptographic algorithm. So this is not just an idea. A lot of work by these large businesses has already been done. And the idea is like even if there's so much adaptability, a lot of CISOs, a lot of security architects, engineers still are not aware about this quantum attacks and PQC, post-quantum cryptography, right? And this was part of the reason why OpenSSL, me and Paul, came here to bring this idea of PQC into the audience in Japan. And hopefully we see more like strong timelines from the Japan government regarding the PQC migration. So TLS was one of the I think one of the greatest example of PQC transition. And since we are here to represent OpenSSL 3.5 now supports PQC, post-quantum cryptography algorithm, like same MLCAM, MLDSA, and SLSDSA by default. So if you are using OpenSSL, which I think everyone uses, whether they are aware or not aware about it, but everyone uses OpenSSL. And if you're using a newer version of OpenSSL, let's say 3.5 and greater than 3.5, you will by default use MLCAM in any of your TLS connection. So before that, for example, if I head to terminal, just to show you guys how OpenSSL is using. By the way, if you have any laptop, you can also run this command, OpenSSL version, and you can see the OpenSSL version that I'm using is 3.5.25, and from the slides you can see from 3.5 and the release greater than 3.5 by default uses post-quantum cryptographic algorithms. So let us say if I try before trying a connection with any of the website, or for example, let's see what algorithms does OpenSSL have. So these are the CAM algorithms. These are key encapsulation mechanisms, and you can see MLCAM. MLCAM is there. So for your key encapsulation mechanism, for TLS, let's say you do the key exchanges, right? For that, for now, we were using RSA elliptic curve cryptography. Now we will use MLCAM. And this is just for the key exchange. For now, let's say for signatures and certificates, we once again use RSA and elliptic curve. Now for those cases, people will use signature algorithms. So these are a bunch of signature algorithms that you can use. And if you focus here, you can see SLS DSA is also there. And if I try to find MLDSA, yes, you can see MLDSA is also there, along with these many algorithm supports. Right? Now let us try to make a TLS connection with any web server, let's say any websites that you usually visit. For example, there's a website called example.com. So we will try to do this TLS handshake, try to build up the TLS connection with this website. And for that, we will using OpenSSL client. It's just like a command line utility that you use. And if I try to make a TLS connection, you can see these are the negotiations. This is your negotiated TLS 1.3 group. It is using X25519 MLChem 768. As of now, that was not the case since I'm using OpenSSL 3.5. This is MLChem 768. Now you might ask, okay, I was talking about MLChem 768. Why this X25519 is still there? By the way, X25519 is a classical cryptography still. But you know, like now some people won't be very much happy with the directly transitioning, like completely transitioning to PQC. So they still need like both the security of the algorithms that we're still using as of now, and the future set of algorithms. So we are using in a hybrid mode, using classical cryptography as well as the newer PQC cryptography algorithms. So we are using X25519 along with MLChem 768. And this is by default. So if your web server, if you're providing any of the services to your customers, for the TLS connection it does not uses MLChem 768, then the answer is you are not quantum safe. All the data that is being sent from client to your application services that you're providing to the customers is not quantum safe, which is not a good idea. So, and this is command line utility. If you simply want to go to your web browser, for instance, let's say if I just go here and if I try to access any other website, for example, Luminary, sorry. This is the conference page, and if you just do right click, you go to the inspect section, and under this privacy and security section, you can see it says it is using X25519 MLChem 768. So it's really good that Luminary, anyone who visits Luminary websites is quantum safe. Cool. Now give me some more example, websites of your company. Give me a few more examples. For example, I mean, there's GitHub.com, I think still does not use post-quantum cryptography. Yeah, you can see even though it uses TLS 1.3, but it's still relying on X25519, which is not quantum safe, right? And let's say OpenSSL.org, I think it should be quantum safe, but it will be. Let's say if it's not quantum safe, then I think it's not going to be good for our image. No worries. Anyways, still see. So OpenSSL.org is not quantum safe. But still, I think the website, the server that is running OpenSSL.org, even though OpenSSL 3.5 has quantum safe algorithms, the server which is on which this public interface is running on, it's not using, I think, OpenSSL 3.5. And let's open any Japan government or any university, let's say University of Tokyo. Then it's quantum safe. It's good. And I don't know whether Japan government. So yeah, so it's also quantum safe. Now give me a few more examples just to just to find some more example of websites which are not using PQC. Facebook.com. I think I might have logged in Facebook, so I should not do this. But yeah, Nicholas, what's your website? Yeah, sorry, what's your name?
Inference-org.
Spell it out for me.
Inference.
INFERENCE.
Yes. Hyphen
LANG.
Lang, like language. Lang.org. Yeah.
Good. It's quantum safe.
I think because what's the program name? CERT.
Maybe you might be using certificates from Let's Encrypt, maybe.
No,
Yeah.
I forgot the name of the. I mean, the tool that we use to generate certificates, it might by default use it, right?
Yes. Let's Encrypt. About what? Can you spell it out for me?
Yeah.
KR
EM
LI
N
N .ru.
Yeah.
Okay.
Because in Russia, I think there is different set of it's not your eyes.
It's not even. It does not even have certificates, I think.
The thing is, like, there is a special set of like certifications that is specific for Russian
Yeah.
website.
Oh, okay. But I think by default it should have open.
It's something like Chipovnik, Kryžovnik, some different algorithms. But maybe not on this website.
I think it's having some issue. Let's University of Tokyo. We did it already, right? So yeah, I think University of Tokyo, the condition is even worse because they are still relying on TLS 1.2. And TLS 1.2, like, you can't even integrate PQC with that. So it's like two things for them. First, they need to migrate to TLS 1.3 and to the version of some, if they are using some library like OpenSSL, then to a version that is greater than 3.5 or equal to 3.5.
Actually, like, can we check Keio University?
KL University?
Keio, Keio University.
So yeah, I think they're using MLChem
Okay.
768. So good for them that they are quantum safe. Oh, I haven't opened it yet. Okay. Okay, they are not on quantum safe. Yes.
Yeah, so I need to inform them about this.
Okay, yeah. So these are just for, and these are like the public-facing interface, right, which you can publicly access. Now, within your whole infrastructure, within your different products, now there are internal components also. There will be load balancer, there will be a certificate authority, there will be API gateway. Now, within all those things, we are still relying on quantum safe. We're still relying on classical cryptography. So that is going to be a much more than what exactly that I showed. Those are like the public interface services, right? And another term that is that has become very famous in cryptographic world and PQC world is crypto agility. The idea is like, let's say, if we want to migrate from one algorithm to other algorithm, how flexibly can we migrate to? Otherwise, if you have done like a manual cryptographic implementation, there are some legacy systems. In order for them to migrate to PQC, the whole application needs to be changed. So it's a very hectic task. And in some cases, from my experience in legacy systems, it's not even possible to migrate it to PQC. So in that case, what we need is like a gateway, proxy servers in between. But the definition of crypto agility differs from like company to company, different use cases to use cases. What my idea of crypto agility is like, again, transitioning to classical cryptography to post-quantum cryptography or to any other algorithms flexibly without changing a lot of things in the applications. Because right now, these days, what happens is like our cryptography is coupled with the applications. So your application is somehow managing the cryptography. It says, in some cases, there are manual implementations. In that cases, the transitioning, as I said, whole application needs to be changed, multiple interfaces needs to be changed, multiple API needs to be changed. So now industry is coming up with the idea of crypto agility, where they say like, now you need to decouple your cryptography from the application completely. If not completely, now then in such a way that, let's say, if future migrations needs to be done, then you don't need to change the application. So now they are saying, okay, and one more thing is, we need to create policies. Let me check the time again. Okay, we still have time. The idea is now we need to create policies. Earlier what we used to do, okay, we simply say in the application, hey, run this cryptographic algorithm. Then we change to, okay, now we will have a configuration file from where we will say, select this algorithm, select this algorithm. Now what we are saying is all this security and cryptography needs to be done using policies. Now not even configuration files, we need policies. So what we are saying, we need a set of policies that will manage the whole cryptography in your infrastructure, services, products, applications, and those will be done in a cryptographic layer or a policy enforcement layer. So we are decoupling the cryptography from application layer to another cryptographic layer that will be managed using some policies that we set, right? And for that, we have to do a lot of things. We have to use cryptographic libraries is just one thing. So we need to use now cryptographic library instead of doing the cryptographic implementation. And even if we use cryptographic library, we need to do it in a separate layer from the applications. Because like, to be harsh, like application developers are cryptographically really dumb. They don't know like which algorithm is best suited, what is going on in the cryptographic world. What they know is encrypt, decrypt, sign, verify, that's it. And I think that should be enough for them. Now, the security, the cryptographic should be managed by the security team, the CISOs. And I know like a lot of companies do not even have a cryptographic team, but they have some security architects, of security engineers that now need to take care of these cryptographic. Let's say if it's like a business sensitive thing, then CISO should say, okay, for the business sensitive critical business services, we will use this algorithm. Application developers need to like only know about encrypt, decrypt, sign, and verify. For different use cases, we will have this set of algorithms. So all that things needs to be done on a cryptographic layer. So this is the idea of crypto agility. And that's pretty much it. OpenSSL, since you know open source work through a strong community, so OpenSSL community is there, which last year had like 346 members from different domains, academics, individuals, large businesses, small businesses. And throughout, through this collaboration, we have, the OpenSSL has progressed a lot throughout these years. And this is like a Lumio page, everyone can join. So I request you to use this QR to join the OpenSSL community. So even if, as I said, even if you say we don't use OpenSSL, the reality is you do use OpenSSL. So any technical direction that you want OpenSSL to head to, what is your use cases, what features you would like to bring into the OpenSSL library, what is your feedback, what problem are you facing, all those things can be done flexibly through our OpenSSL community. So I request everyone, and we have some swags here. So after this talk, please come to that last desk and take some OpenSSL swags. And be a part of OpenSSL conference. So every year OpenSSL hosts OpenSSL conference. So this year will be again in Prague. Last year it was October some date in the same venue, Prague. So please book the dates for October 13 to 15. And an official announcement will come soon. So stay tuned. Yeah, that's pretty much it. Thanks.
Yeah.
Any questions?
Thank you.
Any
So yeah, we
feedback?
have time for questions.
Yeah.
Okay.
Thanks for your presentation. I have a question. Do you anticipate that like in next few years, there will be a new quantum computing algorithm that could break, for example, that ML, KAM, or other two?
Yeah, so right now the industry is most feared about two algorithms. One is Shor algorithm. So Shor algorithm is like it was discussed like way decades ago, but the problem with Shor's algorithm was a classical computer was not efficient enough to actually execute that algorithm. So as I said, quantum computers are like really strong. Computation power is too much high. They are doing exponentially work. So Shor's algorithm is best suited for the quantum computers. So if a quantum computer becomes this much stable and scalable that it actually utilizes Shor's algorithm, then these algorithms is going to be broken soon. And there is another algorithm, it's a Grover's algorithm. It's a brute force one. It focuses more on the symmetric encryption, but symmetric encryption, for example, AES, is I think secure enough. The only transition with symmetric encryption is you need to increase the key sizes. Let's say if you're using AES 128, go shift to AES 256. But I think AES 128 is still strong enough. Yeah.
So do you think there will be new quantum computing algorithms?
Yeah, I think there is a very good scope of that. Yeah. If the algorithm is, let's say, even better than Shor's algorithm, then we are like in a big trouble. So I think there will be definitely more algorithms like that, but the only known algorithm right now is the Shor algorithm and Grover algorithm. Yeah.
Okay, thank you very much.
Yeah. Any other questions?
First question is about AWS or some other cloud provider. If they already allow us to use PQC,
Yes.
The question is, what if I enable it on my load balancer? So it will be TLS with post-quantum, but clients are not post-quantum. So will it fall back to RSA?
Yeah, very good questions. That's part of why we use hybrid MLChem. So you see, like with MLChem 768, there was always X25519 attached with it. So by default, it will go try to PQC and shake. And if, let's say, your client does not even support it, or even, let's say, different server does not support it, then it will fall back to the classical algorithms.
Okay.
Yeah.
Thanks. Second one is about the Shor algorithm. So can you take two prime numbers, multiply it, and using Shor algorithm, break it?
Yeah, I think the part of the Shor algorithm...
Can you show us how to break?
Not at the moment.
How to factorize?
Not at the moment. But if you... But if you contact with someone from Fujitsu, so maybe we can try, because they have quantum computers, so we'll see. But there are a lot of resources. If you actually want to see how Shor's algorithm work, then there are a lot of good resources that you can definitely look into.
Thank you.
Yeah.
So maybe one question from me. When you develop the standards and you actually test them, so what do you actually use to see if the standards actually matches with a PQC standard?
Yeah.
So basically, like I'm just asking, like if there's like any quantum computing resources you're using, or you're actually using a simulator of quantum computer.
So actually, there are some companies who try to simulate these attacks, but I think it's not quite there to actually test, because we don't have like quantum computers. But the thing that makes it secure is the mathematics that it depends on, MLChem, MLDSA. It uses a group of lattices. So it is considered that these multidimensional lattices are secure even against the quantum attacks. There are mathematical proofs. If you go to the standardization, you can see. Now, a lot of people are implementing PQC algorithm. Now, how to actually say these are actually the exact implementation? Then for that, the NIST provides, the standardized body provides some test vectors, ACVP vectors. So if your implementation passes all those test vectors, then we can say, okay, yeah, your PQC implementation is stable enough. But the quantum simulation part is still not there, although some companies are trying to do it. But we are still saying, okay, the mathematics that, underlying mathematics that we are using is secure against quantum attacks.
Okay, thank you.